Welcome back, everyone. So in the previous videos, we introduced the concept of chemical formulas, the importance of using the correct element symbol and subscript to determine number and type of atom. The last video, we talked about the use of these polyatomic ions that are in some chemical formulas, and that these polyatomic ions, they're groupies, they act as a group. They travel together. If you have more than one of them in a chemical formula, you need to use parentheses around that polyatomic ion, and you just need to take care when determining number of atom in that molecule to make sure that you use the subscript appropriately. So for example, with CaClO4 2, this molecule has 4 times 2 or 8 oxygens in it. So we used 4 different polyatomic ions in these examples. The next 2 slides list some, well, at least this slide lists from your book some very common polyatomic ions, their name and corresponding chemical formula. You will notice that almost all of them except one are negatively charged. The only one that's positively charged, or that is a cation, is ammonium, which is NH4+. So these are some that are in your textbook. I recommend having that table handy or printing it out from the notes. I've whittled that down a little bit to that chart to these just to tell you that these are the polyatomic ions that are used most commonly in this course. So these are the ones that you will encounter most commonly in questions and in lecture, and when we have the lab, in the lab section of the course that's on nomenclature. Now I can still quiz you on the ones on the previous chart, but these are the ones you're going to encounter more frequently. Okay? So you should know in particular the name and the chemical formula along with the charge that are associated with these. It's going to be really important when we start writing chemical formulas in the next video, and the names are going to be important when we start naming compounds. Before we start talking about how to write a chemical formula once given ions, let's talk about the types of chemical formulas. So the chemical formulas we have been talking about so far, either ionic or molecular, are molecular formulas. And what that means is that those kinds of chemical formulas list the actual number of atoms of each element that are present in a compound. So what that means is that, for example, hydrogen peroxide, H2O2, that means in a molecule of hydrogen peroxide, H2O2, there are 2 hydrogen atoms and 2 oxygen atoms. So molecular formula, actual number of atoms in a compound. Looking at that molecular formula, you can see that if I wanted to further simplify this formula, doing that gives you the empirical formula. Now, empirical formulas can be really helpful to scientists, particularly if scientists are trying to determine an unknown compound, what its identity is. Many times they will do experiments to first find the empirical formula, which is the simplest whole number ratio of atoms of each element in a compound. And then once you find the empirical formula, then you can do other experiments to determine the molecular formula. And later on in the course, you're not going to be doing the experiments, but you're going to be doing problems where you have to determine a substance's empirical formula and then the molecular formula. What you need to know just right now is that the empirical formula for a molecule is the simplest whole number ratio of atoms in that molecule. So can you take the subscripts that are in that molecular formula and further simplify them to get a whole number. So in the case of hydrogen peroxide, H2O2, you can see that you could easily divide both of those subscripts by 2 to give you, when you divide each of them by 2, to give you the empirical formula, which is just HO. Now, there are some molecular formulas that are also empirical formulas because you cannot further divide them into whole number ratio. So, for example, NaCl, that is the molecular formula. It is also the empirical formula. I cannot further divide the implied ones there any further and get a whole number ratio. Another example of a molecular formula would be I'm just making this up, PCl3. There's no common denominator between the 1 for the phosphorus and the 3 for the chlorine to further simplify it. So, empirical formula, simplest whole number ratio of atoms in a compound. Now, both molecular and empirical formulas are important, but neither one of these say anything about how atoms are attached to each other in a molecule. That kind of information, how atoms are attached, is seen in the structural formula, where we either use lines to show bonds or how atoms are connected to each other, or we use a space-filling model to say how those atoms are connected. So for example, CH4, that is a molecular formula. It's also an empirical formula. I can't further divide those subscripts into a simplest whole number ratio. But looking at CH4, I don't know, it's not clear as to are all 4 hydrogens attached to that central carbon, or maybe 2 hydrogens attached to each other and 2 to the carbon. How are these atoms attached to each other? That's where these structural formulas are important, and we will talk a lot more about structural formulas for smaller molecules and how to determine those in Unit 3 and part of Unit 4, mainly Unit 3. For right now, just know that structural formulas, that formula is a picture that essentially shows how atoms are connected to each other. So that's the end of this little vignette. In the next video, we're going to start to take the information about polyatomic ions and monoatomic ions and write balanced chemical formulas, specifically balanced molecular formulas.